Today we're continuing with our buffer and pH lab. We'll be adding 0.02 moles of NaOH into each of our solutions, and this is equal to 0.2 millimoles. I'm going to be working in millimoles today just to make it interesting and avoid some mistakes that I made before with all the zeros. So here in the first beaker we have H plus and we're adding OH minus into this. First question, is there a reaction? The answer is yes. So we do stoic in moles. The stoic in moles is going to be OH minus plus the original H plus, and that will yield water. We're going to do ICF. So what I need is I need my original HCl. So the original HCl molarity equals millimoles over milliliters. I had 5 milliliters. I had a 0.1 molar. So that's going to be 0.5 millimoles originally. So the 0.5 original goes right here. That's in millimoles. I'm adding 0.2 millimoles of OH minus, and there is no water. Well, there's water, but we don't really care about it. So now we're going to go minus 0.2 minus 0.2. So this is 0, and now this is 0.3 millimoles. And now I look at what I have. I just have H plus, so I have a strong acid. So to handle that, I do molarity equals moles over liters. So I'm going to take my 0.3 millimoles over my total of 10 milliliters. That's going to be a molarity of 0.03. And then I just take the negative log. That's the H plus. So negative log of H plus. And that's going to give me a pH of 1.52, which is fairly acidic, which makes sense because we ran out of the base that we added. Okay, now we're going to add OH minus into this beaker, and this beaker already has NaOH in it. So the question is there a reaction between a strong base and a strong base? The answer is no. So what do I have? I have a strong base. When I do strong base, I do molarity equals moles over liters. So I'll do millimoles, milliliters. The total milliliters is 10. Now I need my millimoles. Well, I'm adding 0.2 of the NaOH that I'm adding in. So that's going to be right here. And then I'm going to add that to the amount that I originally had. So let's look at the original NaOH. The original NaOH, I had a 0.1 molar. I had 5 milliliters of it. So that's going to give me 0.5 millimoles. So I'm going to add that to my 0.5 millimoles with the 0.2. That's going to give me 0.7 altogether. When I do the math, I'm going to get 0.07 molar. Now remember, that's the OH minus. So you could take the negative log of OH minus concentration, and that's going to give you 1.15. And then you do 14 minus that, and that's going to give you 12.85 as a pH, which makes sense because it's basic, because you added a strong base to a strong base. So at the end of this, all you have here is OH minus. At the end of number 1, you had a strong acid that was left over, so you just have H plus. Now we're going to add NaOH to acetic acid, and it's going to be 0.0002 moles of NaOH, which again equals 0.2 millimoles. So the first question, is there a reaction when you add a strong base to a weak acid? The answer is yes, stoic in moles. So we write our reaction of the hydroxide and the HA. So the hydroxide is going to react with the HA to make water and the A minus. And when we take a look at this, millimoles, we have 0.2 of the OH minus. Now we need the original HA. So the original acetic acid, the molarity was 0.1, and the volume I had was 5 milliliters. So that tells me I have 0.5 millimoles originally of the acid in the cup right over here. So therefore I'm going to have 0.5 of this millimoles. That's a 0, and this doesn't matter. So now we're going to subtract the 0.2. That's the one that runs out. And when we're all done, we have 0.3 of this, 0 of this, 0.2 of this, and I have a buffer. So I'm going to use the buffer shortcut. So it's going to equal H plus equals Ka times A over B, which equals 1.8 times 10 to the minus fifth. Acid on top, which is the 0.3. You could use millimoles, of course, and 0.2 is on the bottom. So when I get this answer, it's going to be 2.7, 10 to the minus fifth. That's equal to the molarity of the H plus. So now I need to take the negative log of H plus, and that's going to give me 4.57, which makes sense because this is an acidic buffer. And if you take a look at your beaker now at the end, after you've added the NaOH to the acetic acid, you have still some acetic acid left, and you have a bunch of acetate or conjugate base left. Now we're going to move on to the second example right here. Of course, this was adding OH minus into this. Now we're going to add OH minus into that. First question, is there a reaction? The answer is no, because they're both bases. So what do I have? I have a strong base plus a weak base. When that happens, I only care about the strong base. So to do that, I'm going to take moles over liters. I'll use millimoles. So I have 0.2 millimoles over a total of 10 milliliters. So that gives me a molarity of 0.02. This is the molarity of the OH minus. So if I take the negative log of OH minus, that'll give me the POH, which is 1.70. But I want the pH, so I do 14 minus 1.70, and I get 12.30 pH, which makes sense because this is a basic solution. Now let me just point out why we don't care about the weak. All right, this is just a side note here, why we don't care about the weak. So here's the picture. Again, I have in my cup, all I have now is OH minus, and I have the NH3 as well. So I have a strong base and a weak base. Why do I not even care about the NH3? Because if I did, I would have to do ice and Kb for that, right? So why don't we care about the weak base? So here's NH3 would react with water. If I had to do an ice problem for NH3, this is what it would be. It takes an H from water to make NH4 plus, and of course it would make some OH minus. And I would do ICE. Now I need to know my original molarity of the NH3. Remember, it's going to be 0.05 because 0.1 was cut in half. I don't care about the water. I could get the molarity of the NH4 0 because there was none in there. And then I have the molarity right here of the starting molarity of the OH minus is 0.02. That's what you have to remember to put in. A lot of people forget that. So I know what's going to happen. You're going to put your minus x plus x plus x. And when you're all done, this is going to be 0.05 minus x, x, and 0.02 plus x. And then what do we end up doing? We end up ignoring that and ignoring that. So we're still going to end up with a 0.02 for the OH minus, as long as the Kb is very small, which it is, because the Kb, as you know, is 1.8 times 10 to the minus fifth. So we don't bother doing an ice problem for the weak if we already have a bunch of the strong. That's why we only care about the strong when we have a mixture. Now we're going to add 0.0002, 3 zeros here, moles of NaOH to each of these cups, which is equal to 0.2 millimoles of OH minus. So recall in number 5 that we ended up with water. If we add OH minus into water, all we're going to have is a strong base. So all we care about is molarity equals millimoles over milliliters. So we're going to copy down our millimoles, which was 0.2. We're going to copy down our milliliters, which is 10. That gives us a molarity of 0.02. And remember, this is the molarity of the OH minus. So you need to take the negative log of OH minus, which will give you 1.70, which equals the POH. So then you do 14 minus 1.70 will give you a pH of 12.30, which is fairly basic, which makes sense because you added a base to water. So if you look at your cup at the end, you're just going to have OH minuses floating around. Now let's take a look at number 6. Let's redraw what we should have had in the beginning. Okay, we'll draw the beginning beaker was HA, which is the weak acid, and A minus. This is my initial that I had because I had this weak acid with its conjugate weak base. Now, in the second part, what I'm going to do is I'm going to add OH minus into this buffer. And the question is, will there be a reaction? And the answer is yes, because anytime you put an acid or base into a buffer, you're going to get a reaction. So now you're going to do stoichiomoles. So we'll find our OH minus. It's a base, so it wants to react with the acid. The acid is the HA, and that's going to form A minus and water. We do our ICF chart. The millimoles is 0.2 of the OH minus. Now we have to get the original of the weak acid and the weak base. So let's go over here, give ourselves a little room. So my original of HA is going to be 0.1 molar. I had 5 milliliters, so that's going to be 0.5 millimoles of HA. My original A minus is the same calculation, 0.1 molar, 5 milliliters, so that's 0.5 millimoles of that. So I write these numbers over here, 5.0 millimoles. HA was oh, I wrote that wrong, I'm really sorry. Millimoles. Should be 0.5. So this is 0.5. The A minus is 0.5. I'm trying to avoid problems with these zeros by using millimoles. Okay, so we're going to get rid of all 0.2 of the OH, add 0.2 over here. We don't care about the water. So that's 0. This is 0.3 and 0.7. Now I have a buffer because I have both a weak acid and its conjugate base. So therefore I'm going to use the buffer shortcut. I'll use the Ka shortcut since I know the Ka. So 1.8 10 to the minus fifth. I put the acid on top, which is the 0.3. I put the base on the bottom, which is the 0.7. And I do the math for that. I'm going to get 7.7 times 10 to the minus sixth molar. And that is going to be my concentration of H plus. So if I take the negative log of H plus, I'm going to get 5.11 as my pH, which is acidic, which makes sense because this is an acid buffer. So if I take one little picture at the end of this, I'm going to have at the end still a buffer. I did not wreck my buffer Even though I added OH, I didn't add too much, so I still have a buffer. Now we're on number 7, where we're going to continue to add 0.0002 moles of NaOH to each of these cups, which is the same as 0.2 millimoles of OH minus. So now we have a buffer in number 7 from our original beaker, and we're going to add OH minus to this, and we're going to ask ourselves, is there a reaction? And by now you should automatically know the answer is yes, because every time you add an acid or a base to a buffer, you will have a reaction. So we're going to do stoichiontangent moles. So I just added OH minus to my buffer. Since OH is a base, it's going to find the acid part of the buffer, which is the NH4 plus, and it's going to form NH3 plus water. We're not going to worry about the water. We're going to do an ICF chart. I added 0.2 millimoles of this. Now I need to know the original millimoles of my acid and base. So I'll do that over here. My original moles of NH4 plus came from the molarity equals millimoles over milliliters. I had 5 milliliters. I had a 0.1, so it's going to be 0.5 millimoles, which goes right here. The NH3 originally was also 0.1 molar, also 5 milliliters. So that's going to also be a 0.5 millimoles. So that is going to go right over there. Okay, so I was looking for the millimoles to put in my equation. Now I realize that the OH minus is going to run out. So that's 0.2, 0.2, and plus 0.2. This is running out. I have 0.3 of this, and I have 0.7 of the NH3. Now I have a buffer because I have a weak base and its conjugate acid. So I'm going to use the buffer shortcut. I will choose to use the OH minus simply because I already know the Kb. So the Kb is 1.8 10 to the minus fifth. Then I'm going to take the base, which is the 0.7, over the acid, which is the 0.3, and that's going to give me my OH minus concentration, 4.2 10 to the minus fifth molar. That is the concentration of OH minus. So if I take the negative log of OH minus, that's going to give me a 4.38. But remember, that is the POH. So 14 minus 4.38 is going to equal 9.62, which is the final pH, which is basic, which makes sense because this is a basic buffer. And if you want to take a look at the final drawing, you still have a buffer. You did not wreck your buffer. So you still have NH3, you still have NH4 plus, and the pH is pretty similar to what it used to be. Okay, we're going to move on to the second example on this page, which is number 8. I have a buffer from number 8 that I formed, and now I'm going to add to that the hydroxide. So is there a reaction? The answer is yes. Stoichiontangent moles, because whenever you add an acid or a base to a buffer, there will be a reaction. So I'll write the reaction. The OH minus is going to find the acid part of the buffer, which is HA, to form the basic part of the buffer, which is the A minus, and you will also have water, which we're not going to worry about that. Then we're going to do ICF. We have our 0.2 millimoles of that. And I actually already have my originals over here, so I don't have to recalculate it. My moles right here, this is moles, so I could do millimoles. 0.25 millimoles of the acid, 0.25 millimoles of the base. So we're going to write over here 0.25 millimoles. This one is 0.25 millimoles. I'm going to subtract the 0.2, which is the limiting reagent, minus 0.2 plus 0.2, So when I'm all done with this, I'm going to have 0.3, or rather 0.0. Just see something here. Yeah, 0.05. Sorry about that. And then this is 0.45. And then now I need to take my buffer shortcut because I know I have a buffer. So that's going to be H plus equals Ka times A over B. Move this over a little bit. So I'll plug in my Ka is 1.8 10 to the minus fifth times the acid, which is the 0.05 millimoles, over the base, which is the 0.45. I'm going to have to actually do this on a calculator because I wrote something wrong before. 1.8 negative fifth times 0.05 divided by 0.45 equals 2 times 10 to the minus sixth. Now remember, that's the molarity of the H plus. So then we're just going to take the negative log of H plus, and the negative log of this answer equals 5.70, which is fairly acidic, which makes sense because this is an acidic buffer. So when you look at the final beaker, you're still going to have HA, you're still going to have A minus. Now let me just remind you that this pH of 5.70 is kind of far off from the original, which would have been 4.74 over here. So 4.74 pH of the original buffer. Notice that we're changing by almost a pH unit to 5.70. And the reason for that, as we discussed in a different video, is that we are almost wrecking our buffer. See, this O5 is like almost gone. You took off 0.2 out of 0.25 of the acid part of the buffer. So you really decreased the acid a lot. So now the pH is starting to change more drastically. You haven't wrecked it, but you're getting closer. Lastly, on number 9, we're again going to add 0.0002 moles of NaOH, which is equal to 0.2 millimoles of the OH minus. So recall that we formed a buffer. Let's review briefly. We added H plus originally into NH3, which is a weak base. A weak base and a strong acid are going to react. You created a buffer by turning some of the NH3 into NH4 plus. So this is the buffer that we had at the end of the initial calculation. Now what we're going to do is we're going to add OH minus into this newly formed buffer. And we're going to ask ourselves, is there a reaction? And by now you know that the answer is yes, because anytime you add an acid or base into a buffer, you will get a reaction. We do stoichiontropy moles. The hydroxide is going to find the acid of the buffer, which is the HA, since OH is a base, and it's going to form the A minus and the water, which we won't really concern ourselves with right now. So this is 0.2 millimoles. We also already know the millimoles of the NH3 and the NH4 plus. I did this in millimoles last time to just get rid of some zeros there. So the HA is 0.25 millimoles and the A minus is 0.25 millimoles. The limiting reagent is going to be the OH minus. So minus 0.2 minus 0.2. Oops, I meant to do that in black. Oh well, 0.2 and then plus 0.2. So that's a 0. This is a 0.05 and this is a 0.45. Now look at what you have. You have a buffer. So we're going to use the buffer shortcut. I'm going to use the, oh man, all right, sorry about that. I wrote I don't like when I do this HA for ammonium. It's not mathematically wrong, but I'm just going to change it. Sorry about that. This should have said NH4 plus. You shouldn't really use the A minus and the HA for this. I just wasn't paying attention. I'm sorry. Anyway, NH4 plus and NH3. Still the same thing. Now, buffer, I'm going to use the OH minus shortcut equals KB times B over A. So that's a 1.8 10 to the minus fifth times the base, which is the 0.45, over the acid, which is the 0.05. And you do that math, and you're going to get an answer of 1.62 10 to the minus fourth. And that is the concentration of the OH minus. That's the molarity. Now you're going to take the negative log of OH minus, and that's going to give you 3.79. That's, of course, the POH. Then you have to take 14 minus 3.79 to get your final answer of 10.21, which is the pH, which makes sense because this is a basic buffer. It has NH3 and NH4 plus. We have not wrecked our buffer. I will point out that the original pH of this buffer right here, this buffer should have had an original pH of 9.26. So this was 9.26 original pH. We could have gotten that from the shortcut earlier. Oh, well, actually we got it right here. It was right here. So that's the original pH. Now look at what happened. It turned from that to 10.21, which is almost a whole pH unit, which is a little bit large for, this is really inconvenient, really large because you almost wrecked your buffer. You got this 0.25 turned into 0.05. What I was trying to say was that the NH4 plus of 0.25 turned into a 0.05, so we almost took away all the acids, so we almost exceeded the buffer capacity. Usually they're not going to say wreck the buffer, they're going to say exceeded the buffer capacity, so we're almost exceeding the buffer capacity.